Welcome to G Fun Facts Online. For all of human history, we've had a neighbor we've only ever seen one side of: the Moon. Due to a phenomenon called tidal locking, one hemisphere of the Moon perpetually faces Earth, while the other, the far side, has remained a complete enigma. It's often mistakenly called the dark side, but its true darkness was in our ignorance, until now. In a staggering feat of engineering, China's Chang'e-6 mission has ventured into this hidden territory, landed in the largest crater in the solar system, and returned with the first ever samples from this alien landscape. On June 25, 2024, nearly 2 kilograms of precious lunar rock and dust completed a 53-day journey back to Earth, and the secrets they hold are already rewriting the story of our Moon and the violent history of our solar system. Let's break down what we've learned. The mystery of the Moon's two faces is one of the most fundamental puzzles in planetary science. When the Soviet probe Luna 3 first sent back grainy images of the far side in 1959, scientists were shocked. The familiar dark plains of volcanic rock that formed the Man in the Moon on the near side were almost completely gone. In their place was a rugged, heavily cratered, ancient-looking world. The Moon was two-faced. We later learned the crust on the far side is significantly thicker than the near side. The near side is also home to a unique geological province, rich in heat-producing radioactive elements like potassium, thorium, and uranium. These elements act like a planetary electric blanket, generating heat through radioactive decay, which in turn melts rock and fuels the massive volcanic eruptions that created the dark plains, or Maria, we see. But why was the Moon so lopsided? The leading theory goes back to the Moon's violent birth, in what's known as the Giant Impact. Shortly after a Mars-sized object slammed into the early Earth and formed our Moon, it was a molten ball of rock. As it cooled, the immense gravity of Earth pulled on it, causing the crust on the side facing us to become thinner. This allowed the last dregs of the magma ocean, which were rich in those heat-producing elements, to concentrate on the near side, setting the stage for its distinct volcanic future. The far side, with its thicker crust and fewer radioactive elements, cooled faster and became a geological fossil. To find ground truth for this theory, you'd have to go there and bring a piece back. That was the primary goal of Chang'e-6. The destination was no random spot. It was a place planetary scientists have dreamed of visiting for decades: the South Pole-Aitken Basin, or SPA. The SPA Basin is a feature of almost mythical status. It is, simply put, the largest, deepest, and oldest confirmed impact crater in the entire solar system. At 2,500 kilometers across and over 8 kilometers deep, it's a gaping wound from the Moon's infancy. The scientific reason for going to SPA is threefold. First, it's the largest. Studying a megabasin like this gives us a real-world lab to understand the physics of the colossal impacts that shaped every world in our solar system. Second, it's the deepest. The titanic impact that created the basin billions of years ago would have blasted straight through the Moon's crust and dredged up material from the lunar mantle below. For decades, scientists have wanted a piece of the Moon's mantle, as it holds the fundamental chemical blueprint of the Moon's interior. Chang'e-6 offered the first real chance to get it. Third, it's the oldest. Pinpointing the age of the SPA basin is critical for calibrating the timeline of the entire solar system. The early solar system went through a period of intense violence called the Late Heavy Bombardment. Dating the SPA impact, which is thought to be even older, provides a, quote, golden spike in lunar history, allowing scientists to more accurately date other surfaces on the Moon, Mars, and Mercury just by counting craters. This helps us understand when our cosmic neighborhood finally became stable enough for life to emerge on Earth. The 53-day Chang'e-6 mission was a breathtaking ballet of precision engineering. After launching on May 3rd, The lander and ascender separated from the orbiter and began their perilous descent. Landing on the far side is incredibly difficult. Not only is there a communication blackout with Earth, but the terrain is far more rugged. The lander used a sophisticated suite of sensors to map the surface in real time, dodge boulders and steep slopes, and find a safe spot to touch down inside the Apollo Basin, a smaller crater within the vast SPA. Once on the surface, it had just 48 hours to work. It used a robotic arm to scoop up surface soil and a drill to retrieve a core from 2 meters deep. In a symbolic touch, the hole left by the sampling formed the Chinese character for China. Then came the hardest part, the ascent. Carrying nearly 2 kilograms of samples, the ascender module had to launch from atop the lander and reach lunar orbit entirely on its own, a fully autonomous maneuver without real-time control from Earth. On June 6th, it successfully rendezvoused and docked with the orbiter, transferred its precious cargo to a return capsule, and was jettisoned. After waiting for the right moment, the orbiter fired its engines for home. On June 25th, the capsule performed a skip re-entry, bouncing off the atmosphere to slow down before parachuting to a perfect landing in Inner Mongolia. None of this would have been possible without an unsung hero, the QUE-QIAO-2 relay satellite. Launched weeks before Chang'e-6, its name means Magpie Bridge 2, from a Chinese myth about a bridge of birds that unites lovers across the heavens. QUE-QIAO-2 is China's communications lifeline to the lunar far side, sitting in a unique, highly stable elliptical orbit that allows it to see both the landing site and Earth at the same time for long periods. But it's more than a relay antenna. It's a science platform in its own right, studying Earth's magnetic field and space weather, showcasing how China is building permanent infrastructure in space with each mission. In a significant act of global cooperation, the lander also carried instruments from Europe. A French instrument named DORN measured radon gas seeping from the lunar soil to understand how dust and other materials move across the surface. A Swedish and European Space Agency instrument called NILS was the first ever to detect negative ions kicked off the surface by the solar wind. And a passive laser retroreflector from Italy will now serve as a permanent, high-precision positioning marker on the far side. So after this historic journey, what have we learned? The initial results have been published with remarkable speed, and they are already game changers. Scientists studying the basalt, or volcanic rock, in the samples found evidence of 2 distinct volcanic phases on the far side, one 4.2 billion years ago and another, much more recent one, 2.8 billion years ago. This shows that volcanism on the far side lasted for at least 1.4 billion years, far longer than many theories predicted. The Moon today has no magnetic field, but its ancient core once generated one. By studying the magnetic signatures locked in the rock, scientists found evidence of a surprisingly strong magnetic field 2.8 billion years ago. This suggests the Moon's internal dynamo didn't just fade away. It likely fluctuated, pointing to a much more complex thermal history. Perhaps the most significant finding is that the mantle source for these far-side rocks is significantly drier, with lower water content, than the mantle on the near side. This is the first direct sample evidence for an uneven distribution of water deep inside the Moon, adding a crucial piece to the puzzle of the Moon's fundamental asymmetry. Finally, by analyzing rock fragments believed to be melted by the original impact, scientists have provided a definitive radiometric age for the South Pole-Aitken Basin itself, 4.25 billion years old. This is the golden spike planetary scientists have been waiting for. It is a new, solid anchor point that will be used to recalibrate the age of every major event in the early solar system. The success of Chang'e-6 is more than a scientific triumph. It's a profound geopolitical statement. As NASA pushes forward with its Artemis program to return humans to the Moon, supported by a large coalition of nations, China is building a parallel framework. In partnership with Russia, It is leading the International Lunar Research Station, or ILRS, a planned permanent base at the lunar South Pole. The Chang'e program is the step-by-step execution of that plan. Chang'e-7 will survey the South Pole for resources like water ice in 2026. Chang'e-8, in 2028, will test technologies for 3D printing structures with lunar soil. This new era of lunar exploration isn't about planting flags and leaving footprints. It's about establishing a sustained presence and controlling resources, which could translate into immense strategic influence for decades to come. The 1,935.3 grams of rock and dust that Chang'e-6 brought home are Rosetta Stones for deciphering the Moon's deepest secrets. They paint a picture of a far side that was volcanically active for longer than we knew, with a core that sputtered and surged before it died. We now have direct proof that its mantle was drier and chemically scoured by an ancient impact we can finally date with confidence. The journey of Chang'e-6 has ended, but the journey of discovery it has enabled has just begun. As scientists from around the world begin to tease out every secret held within these alien grains, they are writing new chapters in the story of our Moon, our Earth, and our shared origins. The far side is hidden no more, and our Moon will never look the same again.